Okay, I guess we can get started. Welcome to the physics colloquium. Today is a special colloquium because it's a named lectureship endowed by the Biard family. So this is a Biard lectureship. And so I'm very, very pleased to tell you today we are having Professor Dmitri Basov from Columbia University to give this Biard lecture. But just because this is an endowed lectureship, so let me give you a very brief description about this gentleman, Captain Forrest Tex Biard. He and his sister here, he and his sister actually endowed this funds to Caltech in honor of their parents. And so Captain Biard is a very special person. He actually, he was a physicist and he was a physics professor after he retired from Navy. He actually was involved in decoding the secret codes of the Japanese, and then so that US was able to win the war, they were able to ambush the Japanese carriers during the World War II, the Midway battle. And so he was one of the key people responsible for decoding it. And so there are many other important things he did during his naval career. But for instance, after he decoding that important Japanese codes, then he actually went on with General MacArthur to Australia, and then to also decode a bunch of things. I won't go into the details, but you just know that he had made very, very important contributions during the World War II. And also later on, he was actually an operational officer for the first thermonuclear bomb test. But then afterwards, post-Navy career, then he came back as a physicist. So he was a physics professor at Long Beach City College, and he developed very interesting courses and videotaped them and showed them on public television. So people call this the early version of MOOC. And then he was very interested in quantum physics, cosmology, and astrophysics. So this Biard lectureship actually was endowed both for physics and astrophysics. So there are two Biard lectureships for physics and astrophysics. And the reason was that in 1961 and 62, he actually took sabbatical here at Caltech, and he really enjoyed his experiences at Caltech. And so he endowed the funds, and so that we can invite wonderful visitors like Dmitri here to give lectures. So, okay, so that's that about this introduction. And then, so now I'm going back to introduce our speaker today. So Professor Dmitri Basov from Columbia University. He is really a pioneer and leader in studying electronic properties of quantum materials using nano-optical techniques. His group actually developed a lot of new technologies to do such studies. So you will learn from him, you will think optical techniques are long wavelengths, but he can go down to nanoscale using magic. No magic is physics, but he will tell you about it. So yes, he is a member of the National Academy of Sciences since 2020. He's an APS fellow, and he has won all kinds of major honors, including like the Gordon and Betty Moore investigator in quantum materials from 2014 to 2019, and then again from 2020 to 2015. He also won this high honor from DOD, the Vannevar Bush Faculty Fellowship in 2019. And then in his tender youth, he won the NSF Career Award in 1998. So yeah, without further ado, let's welcome Professor Basov for an interesting talk today.
Thank you for this introduction. It's a privilege to give a colloquium here. Thanks to the Biard family for their wonderful endowment for Caltech. Thank you all for finding time to attend this talk. I know everybody's schedules are very busy, and I really appreciate your finding time to attend this. So okay, how do I kill this one? Maybe I can. I'm afraid to push too many buttons because it's kind of not the best angle for me to read. So where is hide?
Oh, we're trying to remove that bar.
Oh, yeah, you can just,
okay.
you can't remove it, you can only move it.
Okay, so let it sit here. Okay, hope Zoom attendees can hear me as well. So this talk will be about nano-light. True to its label, nano-light is extremely compact, but you have a very bright projector and big screen. I hope you all will be able to see nano-optical images even from the back of the room. Let me start with a headline. In my group, that we were warned that advancing may be an issue. Okay, now it works. So we are developing new nano-optical methods in our group to study new physics in new materials. Optical methods are really pervasive in daily life and in modern technology, and conventional far-field optics is probably one of the most informative techniques that we have in all of physics, and it's widely used in material science and in chemistry and biology. It's really, one of those genuinely multidisciplinary tools. Can you hear me in the back, by the way?
Yeah.
Thank you. So really a universal probe, but quantum materials that are in the vanguard of current work in at least in condensed matter physics, we encounter certain problems, and the problem is that features that we are trying to investigate and study in quantum materials are often very small, much smaller than the wavelength of light. And so we have this problem of mismatch between characteristic energy scales that we study and the wavelength of light that we are using in conventional optics experiments. And this problem is particularly acute in infrared range, where the wavelength of light can be 10 and 100 or even 1,000 of microns. And at the same time, we are trying to investigate effects that are occurring at nanometer length scales. You can say, well, why don't we use shorter wavelength light? And that's a fair comment. But infrared light is very informative because many important energy scales in solids actually fall into this frequency range. So if you want to study superconductivity or magnetic resonances or phase transitions, we have to use long wavelength, very long wavelength radiation. And so we are facing a small problem with that, and a small problem that is that with conventional infrared methods, you cannot see anything small. And that's where nano-light comes to the rescue. My favorite version of nano-optical spectroscopy, imaging and spectroscopy, is a combination of a light source and of a scanning probe tool. And the idea of this experiment is very simple. The idea is that you collect useful signal just from the area underneath this tip. We like to call them optical antennas, but this is really a tip of an atomic force microscope or of a scanning tunneling microscope that several groups here are using. And the rest of the optical path is in the free space. And so, and it's not advancing. And the rest of the optical path is in the free space, and so you can create this maps of 2D contrast of the contrast using this approach. So the wavelength can be anything. So with this and with commercial chips, you get antennas, you get the length scales of a few nanometers very easily. So you beat the diffraction by many orders of magnitude. So this image here may seem like a cartoon. It's actually not a cartoon. These raw data obtained with nano imaging. The contrast is formed. These are data for bilayer graphene twisted at some angle. The contrast is formed by domain walls that we find in this more rare modified graphene. The width of these domain walls is few atoms wide, and yet they produce this, and the wavelength of light that we are using is 10 microns. So nevertheless, with this nano-optical methods, we can resolve these domain walls in all their beauty, and we were able to understand the electronic properties of these domain walls, despite the fact that these are atomic scale objects. It's not very often when atomic scale and optics meet in the same sentence. But with the help of antenna-based nano-light, we certainly can arrive to the situation. These data were obtained by Sai Sunko, a graduate student in our group, who has graduated, and now he is doing important coding for Amazon. So he's one of those who is responsible for next package that you order is delivered on time, and maybe even with atomic precision. When we started nano-optical experiments, our motivation was to go to short length scales. And that has worked to the best of our expectation. But through this journey, we discovered that with this nanoscale optics, we really signed up for something somewhat bigger. And we discovered that with nano-light at our fingertips, we can completely reimagine how we use optical methods in the studies of new materials. Also, nano-light helps us to control properties of new materials in new ways and achieve predictable properties. We like to call them programmable properties. And this is a one-slide introduction to programmable properties. This is taken from the review that a few years back we wrote with your colleague David Steer. Thank you, David, for finding time to attend this talk. Here, this slide, for me, this slide is about how lucky we are in condensed matter physics. And that's because it's now feasible to implement on-demand quantum phases in many different classes of materials. I will focus today on these van der Waals materials assembled from atomic layers with some angle between the layers. And if nature doesn't provide us with the quantum phase we wish to investigate, we just go ahead and create it. And this chart summarizes some of the tools that we have at our disposal to create these phases. They're assembled in the order of ascending energy. We start from heterostructuring, and then we go to magnetic fields, and then we go to terahertz fields, and then this part brings us to optical methods of controlling materials. So a very important part of this control is about targeting with intense optical pulses certain excitations that we have in these materials, and then modify the properties of these materials, if only for a short while. A very important goal of this line of research is mode selective excitation. You are really interested in targeting a certain resonance in the material and leave everything else untouched, that's because you are trying to give more light than heat to your material in the process of pumping. This is actually a quote. This is what Polonius says in Hamlet. And if you succeed in giving more light than heat, then a lot of drama happens in your systems, and you end up with possibly light-induced superconductivity, and certainly light-induced magnetism, light-induced phase transitions, light-induced topology, and more. So, but apart from blasting materials with light, there is Dave's group is one of the leading groups in the world in using this line of modifying and controlling properties of materials. Apart from optically exciting materials with light, there is another approach how one can harness light to modify materials in controllable and predictable ways, perhaps a more subtle approach. And that brings me to hybrid light matter modes called polaritons. In spite of their different nature, light and matter can be unified, can hybridize. When light impinges on the material, it's quite common for electrons in the material and photons to hybridize to produce new quasiparticles referred to as polaritons. Experimental implications of polaritons are, I think, most dramatic when you actually use nano-light in for this line of research, as I will show you. You can think of a polariton as a ripple of electron density triggered with light. This is an artist's view of a polariton on the surface of a conducting material, but these do not necessarily light can hybridize not only with electrons. There are other forms of polaritons, photon polaritons, exciton polaritons, and many others. Any dipole excitation actually produces something like this new type of hybrid quasiparticles. And in condensed matter physics, we quite routinely expect very different types of optical properties once we get access to new types of quasiparticles. And polaritonic quasiparticles are no exception to that rule. So let me give you a few examples of emergent properties that are rooted in polaritons. Perhaps the most well-known examples is Bose-Einstein condensation of polaritons discovered maybe about 15 years ago or more. Polaritons can be used as blocks to produce synthetic quantum matter. These synthetic quantum phases, you can, with the help of polaritons, you can mimic or emulate properties of condensed matter systems. You can use polaritons, for example, to reproduce many of the properties of Dirac electrons in graphene, or you can use polaritons to emulate topological effects in systems. This was predicted by Gil Raphael, who is here. Thank you, Gil, for attending this. Thank you for predicting this, first of all. And Gil's predictions were implemented in the group of Moti Segev in Technion, and this is a very popular area of research of topological, synthetic topological matter created out of polaritons. A very interesting and yet controversial line of research is pertains to cavity control of materials properties. In short, you take a material of interest, you surround it with a cavity, like a Fabry-Perot cavity, and then modes in this cavity hybridize with your material, producing polaritons. And then if you trust the numerous theoretical predictions, then the ground state properties of material may be modified. So a literature search returns really spectacular predictions for new ground states produced by cavity modification of materials. Experiments are slowly catching up, so then they're nowhere as advanced as a theoretical prediction yet, but some results are very, very encouraging, and this is from the group of Jerome Feist at ETH in Zurich. He's investigating Shubnikov-de Haas oscillations of two-dimensional electron gas, and when Landau levels are hybridized with cavity modes. The cavity is a little bit different here. It doesn't look like Fabry-Perot. It's more like a resonator on the surface of this this material, this sample, but functionally it's sort of the same physics. And Shubnikov-de Haas oscillations appear to be altered as the result of polaritons activated in this cavity. Today, I will focus on a related topic of engineered electron photon responses, and this will be I selected for this talk non-intuitive optical responses that, for example, include waveguiding of infrared energy in materials where you don't expect normally waveguiding, including very good bulk metals. And this is all enabled by polaritons. As a side remark, I should say that these aspects of condensed matter research have certainly direct connections to what is going on in AMO community, and so polaritonic ideas and discussions and results I think is a good sort of conversation starter between condensed matter people and the AMO community. So all polaritons are very compact. Some are more compact than the others. Polariton wavelengths would be reduced compared to wavelengths of light in free space by 2-3 orders of magnitude. But perhaps even more importantly, polaritons are not static. These are moving objects. These objects can be literally launched by nanoprobes of our instruments, and it is this moving aspect of polaritons and their ability to bring new properties even to quite conventional materials is really my story today. So this is the outline of my talk. I will tell you a little bit more about polaritonic imaging. And then I would like to tell you about a wide variety of polaritons that we have in materials. I will focus on these layered van der Waals materials primarily today. And then I will tell you about non-intuitive optical phenomena, about so-called hyperbolic media, where polaritons particularly shine, I think. In this experiments, we will use non-equilibrium polaritons. We'll create with light pulses a new electronic state in a layered semiconductors, and new modes, light-induced non-equilibrium modes will be used to build polaritons that behave very unexpectedly, I think. And I'll tell you what we learned from these experiments if time permits. I will tell you about polaritonic version of the Fizeau experiment, of the Fizeau drag that we have recently observed in our group. So that's the plan for today. In fact, I'm basically I'm literally halfway done. So the other 90% about this detail. So this is experiments. So I would like to encourage questions anytime. Please feel free to ask me questions anytime. The more the better. No matter how many questions you'll ask, I will end on time. Please.
I'm new to this field, and I'm wondering, how do you actually create these photon? How do you know that they're there and
That's my next slide. So may I postpone the answer?
Yes.
I'm happy to, I'm not trying to sort of, yes, I will, that's literally the next slide. How do we create polaritons? So, there will be an experimental answer in this slide, and there will be more sort of underlying background answer, maybe 2 or 3 slides from this one. So, this is how imaging is done. So we start with the material of interest. We flood the entire scene with light. We like to work with long wavelength light, again, for the reason of this, of matching the relevant energy scales in the materials of interest. And then we put a scatterer in somewhere in the field of view. We, and the tip of an atomic force microscope, or an STM, is a good choice of this scatterer. When it's illuminated with light, it acts essentially as a dipole that radiates wave very much similar to an optical antenna and spreads these waves in all directions. These are light matter modes, so they can only live within a crystal. And so when these modes, when these waves move away from their source, they reach the physical boundaries of crystals, and then they have to come back. And then what happens is that this antenna now converts polaritonic wave into free space photon, sends light to the detector. So all detection is actually using free space optics. How do we know these waves exist on the sample? Well, we do that with raster scanning our optical antenna. These are raw data that we obtained for plasma and polaritons in graphene. So when these polaritons complete their round trip, they form standing waves between the tip and the physical edge of the crystal. So when we scan from the interior to the edge, go through the series of minima and maxima, and that's what our detector reads out in far field. So this is an experimental aspects of observations. I hope this perhaps answers at least part of your question, and there will be more answers in literally 2 or 3 slides away from here. Yes.
So the antenna creating the impurity, that's fixed, and there's another one scanning material.
So you can do it both ways. You sometimes can the fixed antenna, use it as a launcher of polaritonic waves, and then catch the other one with a moving tip. Or you can use the same antenna for launching and for detecting polaritonic waves through this standing wave character, taking advantage of this round trip character of reflected polaritons from the edge of the crystal. This doesn't need to be a physical edge. This could be a continuous material with distinct electronic properties, and then through polaritonic impedance mismatch, effectively, you get reflected waves, and you visualize these objects like this. Did I answer at least part of your question?
Oh.
Thank you. So with this approach, we can rethink how we use with this polaritonic approach. We can rethink how we use optics to study properties of materials. Conventional optics is all about color. So we study how much light of a given color reflected, emitted, absorbed, and so on. And polaritonic nanoscale optics suddenly becomes mostly about shapes. We study how these waves propagate on the surface of materials, and how they become reflected, how they travel through bulk to heterostructures. And the closest analog in condensed matter physics is quasiparticle interference that our friends using scanning tunneling microscopy are using in their work. So we are doing quasiparticle interference in our research, except for the quasiparticle is different. The quasiparticle is this hybrid quasiparticle built of photons and materials excitation. quite commonly, this wave propagation aspect of polaritons is compared to what you actually have physically when you throw a rock on the pond. I think it's a very good analogy, and I have a New York City version of this analogy. So we'll use an El Dorado, the El Dorado building in the Central Park as a cantilever holder. And when light impinges on this optical antenna, it launches waves, spreading them in all directions. You can understand a lot about water by studying waves on water. What we are doing in our work, we are studying waves on interesting electronic materials, and from that real space observations, we are trying to understand properties of electronic liquids in our work. So, so let me tell you a little bit more about polaritons. Focusing on van der Waals materials, but many of these statements will be more generic. So van der Waals materials are layered materials that can be exfoliated down to single monolayer, and they really host an extremely wide and huge portfolio of properties. They can be metallic, they can be insulating, they can be superconducting, they can be what is this? They can be magnetic, ferro and anti-ferromagnetic, and they can also be semiconducting, and they can emit light in the monolayer form. All these electronic effects are associated with very strong dipole active modes that can be used to build polaritons when we hybridize these modes with light. So it's a plasma polaritons in conducting materials. These are phonon polaritons. These are Cooper pair plasma polaritons built out of superfluids, magnon polaritons, and exciton polaritons. I'll mention at least 3 of these today. So this is the gallery of polaritonic imaging that we obtained using this scanning probe techniques, sometimes taking advantage of this round trip behavior. At other instances, taking advantage of placing a scatterer and studying polaritonic waves that emanate from this scatterer. Please.
So previously you made an analog between this technique and quasiparticle interference.
Yes.
And for QPI, if you're at the Fermi energy, like the wavelength is 2 times the Fermi wavelength. What would the wavelength perturbation here?
Thank you very much. So the wavelength is determined exclusively by the oscillator strength of the dipole mode that we hybridize with light and create this quasiparticle. So in the case of plasma polariton, this is Drude weight of free electrons. In the case of exciton polaritons, this is a strength under the excitonic absorption in the spectrum in the phonon. These are charges of infrared active phonons. And that's really, I really thank you for this question, because this really uncovers some of the powers of this technique. So these images that we obtain, they are not just pretty pictures or maybe ugly pictures, depending on your aesthetical perspective. These images contain quantitative information on the strength of this mode, and also on relevant relaxation effects or dissipation and losses and interactions that lead to losses. This all is contained in these images. That's why we are so fond of this technique. Thank you. Any other questions? Okay, what do I have next? So I have next the wavelength of light that we are using this. In all instances, these features are deep below the diffraction limit of light that is used to obtain these images. So going back to the physics of polaritons and in trying to respond a little bit in more details to the question from the very back of this storied auditorium. So here's the dispersion of polaritonic modes. This dispersion has appeared in condensed matter textbooks probably since mid-60s, but only recently it became possible to take advantage of the imaging techniques actually to access very hard to reach regions of the dispersion. So the dashed line here is a light cone, frequency wave vector. This is light cone. It's highly exaggerated angle, slope, and somewhere here you have material excitation. This could be an infrared active photon. This could be an exciton. This could be another mode. In the recent review, we found about 70 different versions of polaritons that are observed in condensed matter and in AMO systems. And this dispersion is a graphical statement of mode splitting that comes from hybridization of light with this material excitation. So energy essentially is partitioned between these two modes. We are primarily interested in this lower branch for the following reason. At very low frequencies and K, these polaritons are not very different from photons. At very high frequencies and wave vectors, this mode evolves fully into material-like character. And somewhere in between, there is a very interesting region where you have this mixed character between light and matter. And in the way to the right of the light cone here, meaning that the wavelength of polaritons is compressed compared to wavelength of light in free space. Nevertheless, there is slope to this dispersion, so you can prompt these polaritonic modes to move and visualize their motion with the help of nano-optical techniques. So in these mixed regimes, it's not wrong to think of photons as of objects being dressed with matter. So we are dealing here with dressed quasiparticles built of light and matter. This could be a matter part, could be again electrons, magnons, excitons, and there are all sorts of options here. These polaritonic modes, they strongly interact one with each other, unlike photons in free space. This is highly valuable. It's difficult to engineer interaction of photons in free space, but for polaritons, it's sort of natural. And the motion, the transport of these polaritons can be easily controlled with electrical fields and even with electrical currents, as we have recently demonstrated in this Fizeau drag experiments. Nevertheless, polaritons can travel despite their strong matter character. Polaritons can travel as rays of light, but deeply subdiffractional rays inside the crystal. They fully preserve their photonic ID, if you wish, and they're amenable to polarization control. They can show entanglement, as was demonstrated very nicely in the group of Harry Atwater here. So these are interesting objects, and the character of these propagating waves. I'm really grateful for this question. The character of these images, it's not just about contrast, local contrast. It's really about quantitative information. This allows us to reconstruct this dispersion relationship that ultimately contains full information about the response function, including oscillator strength and dissipation channels and interaction of polaritonic states. That's why this technique is informative. So how do we image polaritons? So what does this dispersion plot tells us about polaritonic imaging? Well, we start by turning on our infrared laser. We usually like to move the frequency in this interesting region where we have mixed light matter character. And then the tip of the near field apparatus is capable of launching polaritonic waves with wavelength governed by the dispersion. So the purpose of the tip here in this experiment is to convert free space zero momentum light into this high momentum polaritonic modes that can travel on the surface. You can pick up this mode with another tip that's doable in principle, but not very practical. And it's much more convenient to put a stationary scatterer in somewhere in the field of view and do your scanning around the scatterer. So we are doing all of these approaches with two tips we have never tried to work yet. It's sometimes too overwhelming to work. Everyone who is doing scanning probe knows that even working with one tip can be quite overwhelming, but the two tips is just too much. So that's how it works. So let me tell you now about hyperbolic media and hyperbolic polaritons. Hyperbolic response is a common property, really a signature of layered materials that's commonly, almost universally underappreciated. Layered van der Waals materials typically are very anisotropic. In-plane properties differ from out-of-plane properties. And it's quite common to end up with a situation when the in-plane and out-of-plane dielectric function has opposite sign. The simplest example is when you have some resonance mode that has different energy for in-plane and out-of-plane behavior. So a resonance implies change in the sign of the dielectric function. So you end up with two windows where this condition is satisfied, and this is a formal definition of hyperbolicity. So what's so special about hyperbolic media? I think many things are special, and perhaps the most interesting one is non-intuitive phenomena that this hyperbolic electrodynamics enables. Common crystals always bounce light as soon as the dielectric function is negative. That's why metals are shiny. So, and this is a New York City illustration of metal shininess. Light just doesn't go in, so light bounces back. On the contrary, hyperbolic media support a propagating solution and allow for the waveguide modes to travel inside the crystal in the form of deeply subdiffractional modes with very short wavelength. So the isofrequency surface tells us a little bit more about unusual character of this modes. So the isofrequency surface is a hyperboloid. That's where the name is coming from. So this is an open surface. So you immediately get access in this type of media to infinite wave vectors. In practice, they are not infinite, but they're very, very large, limited by interatomic spacing or interplane spacing. Still an imaging device harnessing hyperbolicity gives you some record numbers for sub-wavelength imaging. These ideas were of hyperbolic media came, as far as I know, from the physics of plasmas, and then they were explored and exploited in metamaterials. These are artificial structures made out of metallic, specially shaped metallic resonances. Our group was the first to observe these waveguide modes in a real material. We first did that for an insulator, for boron nitride. That's a material omnipresent in van der Waals community, primarily is in encapsulating layers, but more recently also is a single photon emitter. And then I will tell you about semiconductors, and we are now finding more and more metals, bulk metals that support these waveguide modes. So how can we visualize this waveguide modes? So that's what we do. We put a scatterer underneath the crystal. We illuminate it with light. These scatterers are usually much smaller than the wavelength of light. The purpose, the edges of these scatterers can launch polaritonic waves, and they propagate through the crystal from using conical trajectories. That conical propagation comes immediately from this dielectric function that has opposite signs in the two directions in the crystal. So then once a disk is expected to produce two hot rings on the surface of the crystal. Of course, these polaritons can only live inside of the crystal. They can't escape the physics of polaritons in hyperbolic modes in boron nitride is in lattice dynamics, and in this infrared active phonons in plane and out of plane at two different frequencies. And so you have two distinct windows of hyperbolicity. So these modes can only live inside the crystal, but we can catch them red-handed as they travel from bottom surface to the top if we come with a tip of the near field microscope, and we outcouple these modes, send light to the detector, and the panel in blue and the yellow is raw data of imaging of HBN photon polaritons using this type of an approach. So these are our vintage data from 2014, and since 2014 there was a question whether electronic processes can support the same type of effects, and we recently found several situations when electronic modes, both plasmons and excitons, can support this. And I will tell you a little bit about the work of Aaron Sternbach on hyperbolic exciton polaritons. So he, even though many materials satisfy this condition of hyperbolicity, there are always some practical reasons that prevent one from observing these modes. And for a long time, we couldn't find a natural crystal where this behavior could be of electronic origin, but because we couldn't find it, Aaron Sternbach in our group decided to create it. So he started with tungsten selenide, a layered semiconductor that's has a number of interesting properties, but as far as this waveguide modes, it's totally uninteresting in its equilibrium state. Both the in-plane and out-of-plane components in the intra-gap region are positive, so it doesn't show this exotic electrodynamics. But then Aaron has illuminated it with light, and by carefully choosing the frequency of this optical pump, he can transform the in-plane optical response by photoinducing both carriers and as it turned out, excitonic states. The in-plane component of the dielectric function is transformed into this negative state. So the crystal is expected to be hyperbolic, if only for maybe few tens of picoseconds before this process relaxes and the system goes back to equilibrium. And then we repeated this experiment with imaging of polaritonic waves emanating from a disk underneath the crystal. But now this imaging part is synchronized with pumping, because we are interested to understand the properties of polaritons in non-equilibrium regime when optical pump transforms this crystal into new electronic states with with the response that shows different signs for in-plane and out-of-plane components. So we expect this disk to launch to produce 2 rings on the top surface, and that's what we tried to image. So yes.
Could you explain physically how this function can create in-plane dielectric point zero negative?
Yeah. So our expectation, very naive sort of pedestrian expectation, was that we will create a high density of mobile carriers, and that primarily live in tungsten selenide planes. That was the starting point. This expectation was a good motivation for this experiment, but it was wrong. It turns out, and our theory colleagues, Angel Rubio, whose name is blocked by Zoom, but he's a very important collaborator on this project, and also he was working with Simone Latini. So through the density functional theory work, they were able to deduce that this photo-induced plasmonic response is actually not as anisotropic as we naively thought. On the other hand, there is a certain special type of excitons that's activated by these optical pulses that does produce anisotropic behavior, and bingo. So we obviously we will see this waveguide modes in this blank space. Otherwise, I would have been talking about something else. Yes.
Do you ever polarize the thin that you want the 10 micron line?
Sometimes we do polarize it. So sometimes it's advantageous, especially with experiments when we work with shaped antennas that launch very peculiar wave patterns and spiral wave patterns. So it's useful to polarize it both linearly and especially to pick up one circular polarization with a polarizer and get left-handed and right-handed spirals from polaritonic waves that we observed and studied and enjoyed them for their beauty.
So in this context, the energy is highly relevant, right?
Energy.
Of the pump. Besides certain special excitons.
Yes, energy of the pump is very, very, very important. It was picked up in such a way that we are in the tail of the excitonic absorption, so that we access the exciton. On the other hand, it's the absorption coefficient is such that we still have full penetration of this pump light through the bulk of the crystal before they agitate the entire bulk of the material. So, and Aaron has worked very intensely on selecting the energy of the pump. But
Things like the negative epsilon is to be commonplace. Anytime you're highly anisotropic metal,
almost every layered material should have it or has it. And so why it's not more common? It's actually this loss thing that even though you satisfy the condition for hyperbolicity, you still don't have propagating modes because they're overdamped. And so you have to select a system where these loss channels are decoupled from the frequency range where you study your effects or minimize. This is yes, and that depends. So if you work if you do this imaging at the close to the plasma edge of this of generated carriers, you actually could be in a very good territory where loss is still manageable, but propagation is possible. So this image is obtained in equilibrium state, meaning that the pump light hasn't arrived yet. What do you see in this image? I hope you don't see anything. And nevertheless, it's a more or less uniform contrast. Nevertheless, we know that these antennas, gold discs, sit underneath the crystal. But for the nanoprobe, they're too deep. They are not reachable by the nanoprobe. They're too deep. You cannot sense them with the nanoprobe before you initiate hyperbolicity. And now we do the same imaging. Aaron does the same imaging at short time delays of few picoseconds, and now the two disks that we sort of expect from this these outline are evident in this plot. If you wait longer with your probe after the pump arrives and alters the electronic state of this tungsten selenide, then it slowly is decaying. So the lifetime of this effect is about a few tens of picoseconds. So as I mentioned, our expectation was kind of was naive to create plasma frequency, but with the help of our theory friends, we were able to come up with a more realistic scenario. So a more likely scenario involves transitions between a series of internal orbital excitonic states in tungsten selenide that are known to be there. But these transitions, in principle, they're extremely strong, so they could lead to these strong features. But they need to be activated and that's the role of the pump light. You need to populate this level to enable these interexcitonic level transitions. And that's the scenario that accounts for most features of the data. So from these experiments, from imaging polaritonic waves, we were able to learn new facts about excitons in this tungsten selenide semiconductor. So let's see how we are doing. Just a couple examples of very non-intuitive effects that you can do with hyperbolic modes. You have actually full control with the angle of propagation of these modes, and you can send them almost vertically from your emitter antenna to the top surface, and that allows you essentially, because of that, a slab of polaritonic hyperbolic crystal acts as a lens, as an imaging device. So this is an AFM image of Columbia logos. We place them underneath the crystal. We illuminated it with light. So every element of the structure is launching polaritonic wave that we forced to propagate almost vertically from bottom surface to the top. And I hope you can recognize the image on the top. It's not perfect, but all elements of this image are sort of lambda over 30, which is a good factor. Together with Josh Caldwell at Vanderbilt, we were able to obtain better images with with feature sizes 1 over 150. In other examples, when we hybridize, this is an interesting layered compound, zirconium silicon selenide. It hosts a two-dimensional electron structure that repeats layer after layer. It's 3D bulk crystal. It is strongly anisotropic. The electronic structure is such that it enables a transparency window where where losses are minimized and propagating modes are possible. We observed propagating modes traveling through the bulk of the crystal. We've learned new aspects of the electronic structure of this material from this experiment. polaritonic rays normally abide by the rules of geometrical optics, but sometimes refraction of polaritonic waves could be negative, and that allows you to create circulating modes that travel through a bicrystal. So let me skip the physio part and come straight to the question to the summary. This was about polaritons. With the help of polaritons, we can reimagine how we proceed with imaging. In condensed matter physics, we were able to harness these waves to investigate excitonic effects in tungsten selenide. I didn't have time to discuss drag experiments, but they're extremely cool. But with all these experiments, I think we have basically scratched the surface of what nano-optics can do for us in condensed matter physics. And we are beginning to reimagine what we can do next, what kind of materials we can study, what kind of properties we can investigate, what kind of new physics we can study. It's 5 p.m. sharp based on the clock that I'm following. Thank you very much for being a great audience.
Yes, we have time for questions. Yes.
So, a very nice question. When you experimentally excite these modes, are you confident that you don't excite any other mode?
You excite many things usually when you use light, especially if it's a broadband light. We are fairly confident that these waves, that in wave patterns that we observe, are polaritonic patterns of certain kind. So, and that comes from this confidence comes just from the experimental character, and then this confidence comes from understanding something about the response function of material that may be obtainable either from other experiments or theoretically. So we can there are many means to compare experiment and theory here. So they comply these waveguide modes that we observe, or these wave patterns that we observe. They comply with basic expectations that we have from their propagation in the crystal, or reflection, or refraction in some cases, even negative refraction. So I would say that is the dominant signal that we are investigating. There is always the background. What's hidden in the background is going to be a topic of the next talk.
Maybe I missed it, but when you were showing the control of the angle of the polariton, how do you control that angle?
So you control it with frequency. So this angle is essentially a rate given by the ratio of in-plane and out-of-plane dielectric function. Both are function of frequency because we're working close to the resonance mode. So by selecting the probe frequency that creates this hyperbolic polaritonic quasiparticles, you can design the angle at which it travels.
What's the scan rate of the edge of the image, and other, the ripple image? Is it topography channel or other channel conduction?
I understand the ripple part. So, but the first part was about scan range. Scan rate. Scan rate is incredibly slow. So this seeing this image appearing on the screen is like watching the grass grow. So it's almost literally. So watching your noise grow out of or signal grow out of the noise background. So a good frame takes sometimes up to an hour to obtain. So and we are talking about, you know, maybe micron by micron image, and it takes even longer. So if you want to have enough pixels, so there are ways to deal with that. So there are these you know, this infamous machine learning is actually bringing good news for us, and it allows us to accelerate scanning using certain tricks that you can do. Basically, you can relatively easily develop an intelligent microscope that scans only in locations where you get most information, and skips the rest of the field of view where nothing is happening. Topography, thank you for this part of the question. If you have you know, non-uniform surface, topography could enter into the signal and produce various artifacts. This is almost never the case, or rarely the case, with van der Waals, atomically flat, smooth van der Waals materials that are smooth. So in fact, some local topography ripples that are observed could be very telling, and could lead to interesting properties. This morning we were discussing with my host possible experiments where the whole new physics resides in local topography.
Yeah, thanks for the great talk. I also have a question about hyperbolic estimate. Just based on the, you know, the intensity distribution and the negative morphology of the pattern, can you infer something about, you know, varied defects in the material?
So defects.
If the middle rows say were, it was topographic.
So in some instances, wrinkles can act as launchers of polaritonic waves. If there is, especially if there is an electronic contrast associated with either with a local defect or with a wrinkle, we see that all the time. So with in this case, we are fairly confident these are much more subtle signals than contrast produced by launching of the you know, deliberately introduced scatterer. So in this case, in this pump probe experiments that done by Ernst Sternbach, that are among the probably the most challenging technical experiments that we've done. So these other effects could be there, but we don't see them. We have enough signal to noise to resolve these two really very prominent rings, and other subtle features are maybe there, we don't see them. So defects, of course, always enter as a loss mechanism of polaritonic waves. Even if they don't launch polaritonic waves, they could act as every defect in principle can convert the polariton into free space photon, meaning that we are destroying sort of wave packet, polaritonic wave packet at every defect. So they can contribute to the loss mechanism.
I guess my question is whether you could use that actually as a positive. You use this as a diagnostic theory.
Yeah. So we've seen buried defects with phonon polaritons, and with the axion polaritons we just couldn't do it yet. So
Unless there are other burning questions. Okay, well, let's thank Mr. Basov for an excellent talk.
Great, thank you very much.